everyone. Welcome back. So, we are really working towards being able to eventually understand reactions. And so, in once we start thinking about reactions, thinking about this internal energy and this entropy can get challenging because the constant variables that we're thinking about under those conditions may not be what we're dealing with in the lab. And so, with this, we really need to start figuring out how to think about things, about other forms of energy besides just the entropy or the internal energy. The Gibbs energy is a really key property. And it turns out that this is another measure of spontaneity. So if we think back, that we defined that the Gibbs energy is a function of temperature, pressure, and moles. And it turns out that these are the three things that in experimental conditions that we tend to be working with. And so the Gibbs energy is defined based upon the relationships that we worked out in Chapter 7 as the energy minus Ts plus PV. So if we take the derivative of both sides, keeping temperature and pressure constant, what we have to do is we have to use the product rule. Remember that the derivative of x times y is equal to the first times the derivative of the second plus the second times the derivative of the first. And so if I do this, I get that dg at constant t and p equals dE minus TdS minus SdT plus, PdV plus VdP. Now, since we are holding temperature and pressure constant, this term is 0 and this term is 0 because dt isn't changing and dp isn't changing. So this gives us that dg at constant temperature and pressure is equal to dE minus TdS plus PdV. And so this means that since we need entropy to be a positive value for things to be spontaneous, that when dg is negative, so really we're looking at the drive from this term, when dg is less than 0, the process is going to be spontaneous. And so at equilibrium, the Gibbs free energy is at its minimum value for those conditions. Now, the Helmholtz energy is another measure of spontaneity, very similar to Gibbs, but in this case, we are keeping volume constant instead of pressure. And with the same sort of analysis, we find that when the Helmholtz energy is negative, the process is spontaneous. So, spontaneous processes are not necessarily ones that minimize the energy. So we're talking what's known as internal energy, or the E. The Gibbs energy and the Helmholtz predict spontaneity under common benchtop or body conditions of constant temperature and pressure. And the Helmholtz is constant, I can't spell, T and V. So now, another form of Gibbs is that we can use this relationship of G equals E minus TS plus PV. And we can also use the relationship that H equals E plus PV. And we can combine these two. So we plug this one into here, and we get that G is equal to H minus Ts. And then at constant T, we can do the full derivation. So we've got to use the product rule. And we find that delta G is equal to delta H minus T delta S. Now the key with this is that the values for delta H and delta S that we use have to be at the temperature that we're interested in. And delta S and delta H are values that are reported at constant T, but their number, their magnitude changes at different temperatures. And so we just have to make sure that the temperature that we are interested in and our values for delta H and delta S all line up.